Welcome, geniuses. I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Hi everyone, today we are going to learn about complex number. So let's first start with the Movers Theorem. So the Movers Theorem states that when n is a rational number, cos theta plus I sine theta to the power of n equals to cos n theta plus I sine n theta. Alright, the proof of this theorem is done in 3 stages. Let's look at stage 1, where n equals to all real positive integers. So we can prove this using the proof by induction method. So we start with the first proposition. We say that cos theta plus I sine theta to the power of n equals to cos n theta plus I sine n theta for some positive integer n. And when n equals to 1, we have the left hand side equals to cos theta plus I sine theta to the power of 1, which is equals to cos theta plus I sine theta. Then for the right hand side, we have cos 1 theta plus I sine 1 theta equals to cos theta plus I sine theta. So left hand side equals to right hand side. Hence we say that P1 is true. And then we assume that PK is true. Then the fourth step, we say cos theta plus I sine theta to the power of k plus 1 equals to cos theta plus I sine theta to the power of k times cos theta plus I sine theta. And using the de Moivre's theorem, we change the cos theta plus I sine theta to the power of k into cos k theta plus I sine k theta. We then simplify this into cos k theta times cos theta minus sin k theta times sin theta plus I times sin k theta times cos theta plus cos k theta times sin theta. And we know that the identity for this is cos k plus 1 theta, and the other one is sin k plus 1 theta. So we can conclude that pk plus 1 is true. And since p1 is true, p2 is true, and by induction, pn is true for all n, where n are all positive integers. Now for stage 2, when n is a negative integer. So we let n equals to negative m, where m includes all positive integers. So cos theta plus I sine theta to the power of n equals to cos theta plus I sine theta to the power of negative m. And we know that negative m can be rewritten to become 1 over cos theta plus I sine theta to the power of m. And then we use the Movers Theorem and we obtain 1 over cos m theta plus I sine m theta. So now we want to rationalize the denominator. So we times the numerator with cos m theta minus I sine m theta, and we times that to the denominator as well. And this fraction is now simplified to cos m theta minus I sine m theta. Which is equivalent to cos minus m theta plus I sine minus m theta. Substituting minus m with n, we obtain back cos n theta plus I sine n theta. Hence, the denominator applies to negative integer as well. When n equals to p over q, where p and q are integers, we substitute n with p over q, and we got cos p over q theta plus I sine p over q theta to the power of q. And using the Movers Theorem, we obtain cos p theta plus I sine p theta, which is again using the Movers Theorem, we obtain cos theta plus I sine theta to the power of p. Taking one of the q roots of the relation, cos theta plus I sine theta to the power of p equals to cos p or q theta plus I sine p or q theta to the power of q yields cos p or q theta plus I sine p or q theta equals to cos theta plus I sine theta to the power of p over q. Note that only stage 1 of the proof is examinable. Let us now use the De Movers theorem to express trigonometric ratio of multiple angles in terms of powers of trigonometric ratios of the fundamental angle. So the first example wants us to express cos 6 theta as a polynomial of cos theta. So we write cos 6 theta equals to the real part of cos 6 theta plus I sine 6 theta. Using De Movers theorem, we can change it into cos theta plus I sine theta to the power of 6. We can write cos theta as C and sine theta as S. Then we expand it using the binomials theorem. Since we want only the real parts, we cancel all the imaginary parts out. And we want it in terms of cos theta, so we are going to change all the s into c using the identity sine square theta plus cos square theta equals to 1. And we can expand the 1 minus c squared squared and 1 minus c squared cubed using again the binomials theorem. Which eventually simplifies to 32c to the power of 6 minus 48c to the power of 4 plus 18c squared minus 1. Everything in terms of cos theta. And we substitute the c back and we obtain this expression. The next example wants us to express sine 5 theta as a polynomial in sine theta. So we first express it in terms of cos theta plus I sine theta, and we want it to be imaginary. So imaginary of cos 5 theta plus I sine 5 theta is sine 5 theta. And we use the De Movers theorem again, so we got its identity, which is cos theta plus I sine theta to the power of 5. And we replace cos theta as c and sine theta as s. And then we use binomials theorem to expand this. Since we want only the imaginary part, we cancel all the real parts out. We want it in terms of sine theta, so we don't want the c, and we turn all the c into s using again sine squared theta plus cos squared theta equals to 1 identity. So all the c squared will be turned into 1 minus s squared. Eventually, it can be simplified to 5s minus 20s cubed plus 16s to the power of 5. And we substitute all the s with sine theta, and we obtain our final answer. In this example, we are going to express tangent 5 theta in terms of tangent theta and cotangent 5 theta in terms of cotangent theta. So what do we do first? So we need both cos 5 theta and sine 5 theta. So what we do is we expand both. So using the De Moivre's theorem first, we have cos theta plus I sine theta to the power of 5. And then we use the Polynomial's theorem to expand this c plus is to the power of 5. And in this case, we need both the real parts and the imaginary parts. So the real part is c to the power of 5 minus 10 times c to the power of 3 times s squared plus 5 times c times s to the power of 4, that's the real part. And the imaginary part is 5 times c to the power of 4 times s minus 10 c squared s cubed plus s to the power of 5. So tangent 5 theta is sine 5 theta over cos 5 theta. Sine 5 theta is the imaginary part, and cos 5 theta is the real part. We just copy them down, and we obtain this fraction. But we want it in terms of tangent theta. So we divide the numerator and the denominator by c to the power of 5, where t is the tangent theta. And we can then substitute the t back in terms of tangent theta. For the cotangent 5 theta, we know that it's equivalent to cos 5 theta over sin 5 theta. And cos 5 theta is the real part, sin 5 theta is the imaginary part that we have expanded just now. And we will have this fraction. To express all the cos theta and sin theta in terms of cotangent theta, we are going to divide both the numerator and the denominator by s to the power of 5. And that's our answer.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.